In this video, I'll be walking you through the post-lab data analysis for lab number 2, measuring the charge of an electron. So the first few problems that you're going to do on this post-lab assignment actually have nothing to do with the data that you collected in the experiment. That's going to come a little bit later on the post-lab. The first question is asking you to convert frequency of 1 nanoamp into units of electrons per second. And the conversion factors that you're going to need are right here. So to solve this, the first thing that you're going to do is take that 1 nanoamp and you will be converting that into amps. That's just going to be a conversion out of the metric prefixed unit into the metric base unit. The nano is a metric prefix. So this will be practicing, just sort of the same way you would convert like a nanometer into a meter, just that type of conversion. And then once you get into units of amps, you are going to convert from units of amps into units of coulombs per second. And you'll do that using this conversion factor, which if you look at it closely, kind of like nothing mathematically is happening here. 1 amp is the same as 1 coulomb per 1 second. So in terms of the numbers, nothing is going to actually change in this step. You're just switching up your units. And then the next thing that you're going to do is convert from coulombs per second into electrons per second. And this one is going to involve a little bit of math. The conversion factor that you need is right here. This gives you the relationship between coulombs and electrons. So you're going to take this equality and you're going to use that to set up a conversion factor. It's either going to be 1 electron is 1.602 times 10 to the negative 19 coulombs, or you might use it in the other direction. 1.602 times 10 to the negative 19 coulombs is 1 electron. You have to decide which one of these is the appropriate version based on where your units are located here and where you want your units to end up being located at the end. So this is just an exercise in unit conversion, just practicing stuff we've been doing related to unit conversions. Same kind of thing in question number 2. In this one, you are taking 100 electron volts and you're converting that into units of joules. So you're going to be starting with 100 electron volts and you're going to be converting that into joules. And the conversion factor that you need for that is right here. 1 electron volt is equal to 1.602 times 10 to the minus 19 joules, which means you're either going to set up a conversion factor that looks like this with 1 electron volt on top and the joules on the bottom, or you'll set it up in the opposite direction. 1.602 times 10 to the 19 joules is 1 electron volt. And again, you're going to make that decision based on where these units need to be in order for everything to cancel out the way that you want it. Okay, so for questions 3 and 4, now you're getting into the actual data that you're collecting in the lab. This is asking you to describe something that's happening in the procedure, and it's asking you to describe what happens to the stream of electrons. The stream of electrons is going to move. It is going to change. That's not really what I'm looking for. I want to know where they are moving. Are they moving to the left? Are they moving to the right? Are they moving up, down? Are they getting brighter, darker? Like just, be more specific. Then don't just say they've moved or they've changed or something. But you don't need to be super specific. Don't give me a complete sentence or whatever. It's sufficient to just say they moved to the right. Like that would make me happy. And then question number 5, also, as you do the experiment, you'll be able to answer this question based on, the different steps that you're taking in the procedure. Where should the signal be when the electric and magnetic forces are balanced with each other? So for question 6, this is data that you'll be collecting in the experiment. So you'll be entering in numbers into these 4 boxes right here based on your data. No calculations for question number 6. This is just you reporting your data. And then now we're going to get into kind of the heavy calculations. So the first thing that you're going to do with regards to your data calculation is calculate the charge to mass ratio. ratio. In this type of chemistry, we use the symbol lowercase q to represent the electron's charge, and then we use m subscript e to represent the electron's mass. And you're going to calculate the charge to mass ratio based on the data that you collected in the experiment. So this is the equation that you'll use to calculate the charge to mass ratio. It has a constant built into it. That's the 5.0826 times 10 to the minus 12. You're going to plug in the value of your electric field, which is going to be this number right here. I'm just going to copy it. You're going to plug in D, that's the deflected distance in units of centimeters. So that's going to be this number right here. That's going to go into this spot. And then you're going to plug in the value of the magnetic field in units of microtesla. So just copying this number right here and make sure it's squared. So I'm just going to put some random numbers. These aren't correct. I'm going to say, let's say that my electric field was 2 volts, and let's say that my magnetic field was 3 microtesla. And so if I'm solving this problem for my 5 centimeter data, the charge to mass ratio that I would come up with would be 5.0826 times 10 to the 12 times the volts, which is 2, so I'm taking my data right here, times the distance, which is 5 centimeters for this particular measurement, divided by the magnetic field in microtesla squared. So that's going to be 3 squared, or 9. And I'm just going to plug these numbers in. And then you're going to do the same thing for your 3 centimeter deflection. So that's going to be using the numbers in this spot. And then of course you actually have to do the math on this. I don't have a calculator handy, but you're going to figure out what this is actually equal to. And then we are going to take the charge to mass ratio results from question number 7, and we're going to convert the units on them. So the units of those charge to mass ratio, I actually was very lazy over here and I left my units off. This is a volt, this is a centimeter, and this is a microtesla. So there are units on it, even though I did lazily leave those off. And we're going to convert the volt, centimeter, microtesla squared unit into units of coulombs per kilogram, because those are the standard units that we use when we're expressing the charge to mass ratio. So you're going to do that unit conversion for the 5 centimeter data and for the 3 centimeter data. And this is kind of a trick question. 1 volt centimeter microtesla is equal to 1 coulomb kilogram. So you're not doing anything mathematically here at all. You're just changing the units. If this is a 2, then this would be turned into a 2. If this is a 5, this would be a 5. Nothing mathematically is happening here. And then now we're almost done. The next thing that we're going to do is actually calculate the charge of an electron using your data. So from this part of the problem, we have our charge to mass ratio in units of coulombs per kilogram, so whatever it might be. Down here, you're being told the mass of an electron in units of kilograms, and so you're just going to figure out the actual charge. So let's say this is not accurate data, but let's say here that we calculated, let's say that we had 10 volts per centimeter per microtesla squared. That's going to be equal to 10 coulombs per kilogram. That would be our charge to mass ratio. And then we're going to come down here with that data, 10 coulombs per kilogram, and what we want to do is multiply it by the mass of the electron in units of kilogram, because what we're trying to do is eliminate that kilogram unit completely and just isolate the coulomb unit. Just get it down to charge in terms of coulomb. So you're going to do the math out here, you're going to get coulombs. And last thing that you're going to do is see how accurate your data was. So we know the actual value of the charge of an electron is 1.6 times 10 to the minus 19. Your data is going to be pretty close to that. It's probably not going to be exactly that, but it should be relatively close. And you're going to calculate your percent error. This is the equation that you'll use to calculate your percent error. Your value is referring to the value that you calculated yourself. whatever you got in question number 9. The standard value is this number that I've provided for you. And notice that the standard value is used twice in this equation. These bars represent absolute value. So whether this ends up being a negative number or a positive number, it doesn't matter. I want you to express this as a positive number. You're going to end up with a positive percent error, whatever it might be. You'll calculate it for the 5 centimeter and also for the 3 centimeter. Now, one thing that I do want you to kind of be heads up on is that when you have a really tiny number, like something that's 10 to the minus 19, it doesn't take much for the error to be really high on a small measurement, just because there's not a lot of wiggle room there. So you might get a pretty high percent error here, and that's totally okay. What you want by high percent error, like maybe you get 100% error, that's fine. You know, could be really bad. What you want to look out for is that you should have a number that is kind of close to this number in terms of the order of magnitude. When we say order of magnitude, we're referring to just this part. So if you've got anything that's in the ballpark of like 10 to the negative 18 to 10 to the 20, somewhere in that range, I feel like you're doing all right. Like you're kind of zooming in on that particular measurement. But if you've got down to this point and you have a charge of an electron and it's like 10 to the 50, I mean, that's way, way, way off. And that means that you've done something super wrong. Don't keep powering through on these calculations. Go back and find your mistake and see what you've done wrong. Your result should be in the ballpark of 10 to the minus 19, somewhere in that vicinity. And again, that might mean that you still might end up having a really high percent error, and that's okay. That's pretty normal when we're dealing with numbers that are this teeny, teeny, tiny.